Good morning. Can everyone hear me well? Can you see?
Yes, and we see your slides.
Great. Right, so my name is Gideon. I'm a second-year PhD student at the Max Planck Institute for Astronomy, working with Roy van Boekel and Thomas Henning. My main field of research is observations of protoplanetary disks, specifically with the newly commissioned VLT AMTs. An additional project of ours, which I'm to present here today, it's still a work in progress, is concerned with similar objects, protoplanetary disks, but from a different observational angle, using the VISIR-NEAR configuration as a Longslit spectrometer with a stable, essentially diffraction-limited PSF, which is able to spatially resolve targets in our sample with roughly the resolution of tens of AU, and probe geometrical properties of disks, disk photospheres using N-band PAH emission features. And so without further ado, I'd like to present you with the motivation for our study. Oops. The ability to spatially resolve protoplanetary disks has recently changed dramatically, particularly in the last decades. Nowadays, observation with, for example, ALMA or sphere provide a wealth of detail and trace different vertical layers of the disk, with scattered light observation tracing the disk surface and millimeter continuum observations tracing regions near the disk midplane, and so on. In this plot, the x-axis is the radial distance from the star, and the y-axis is the disk scale height. This plot demonstrates how effective emission height of different tracers vary for a three-dimensional disk, in this case, HD 97048. I'd like to draw your attention to the black curve depicting the effective height emission of PAHs, or polycyclic aromatic hydrocarbons. Contrary to large grains of order millimeter in size that dominate the emission seen in the ALMA continuum images, PAH molecules are strongly coupled to this gas. They are presumably present throughout the disk, but are excited and therefore observable only in regions directly exposed to stellar UV radiation, and thus probe the highest disk layers or their photospheres. In this study, we trace projected geometries of disk photospheres through N-band PAH emission and produce radial profiles. We then check whether our profiles correspond to substructure observed in different layers of these objects. So let's move on to our observational setup. We will use VISIR-NEAR in Longslit spectroscopy mode. The spectral resolution is roughly 450, and the spatial resolution is about 1.1 lambda over d, which is quite awesome. In this plot, you can notice the stable PSF behavior throughout the entire set of observations. The average full width half max is nearly at the diffraction limit with a pretty small scatter. These observations could have been performed only in people tracking mode with a predetermined instrument rotation angle that cannot be changed. A preferred orientation of the slit with respect to target geometry was unfortunately not possible. We ensure that the outer spatial edges of our spectra, which in this plot are depicted by the red stars at the opposite side of the slit center, which is the yellow rectangle, do not get spatially smeared by field rotation. We achieve this by stacking the observations for which field rotation caused a spatial offset at this coordinate by less than a PSF resolution element. Now I'll briefly discuss our target sample. So our sample consists of 8 Herbig Ae stars, some of whose properties appear in the table on the bottom right. The choice of the target sample relied on the following criteria. So they are relatively nearby and are optically bright, which is important for both the effectivity of the AO and the ability to resolve them spatially. Extended spatial emission had been demonstrated for most of the targets in previous studies, and PAH emissions were detected as well. Lastly, the existence of substructure within these targets, such as gaps, was also demonstrated in previous work. I will now skid over our methodology and analysis but very briefly. So in Longslit spectroscopy, the output data corresponds, of course, to the spatial information being dispersed perpendicular to the slit long axis, while the spectral information, while the spatial information in parallel to it. Here, I demonstrate raw detector output, where the x-axis is the spatial dimension and the y-axis is the x-axis is the spectral dimension and the y-axis is the spatial one. The source is roughly centered in the middle of the y-axis. We begin by extracting the raw uncorrelated data for a single row or a spatial coordinate, here seen in this plot. We then calibrate and reduce it to receive N-band emission spectrum, shown here in blue. We then utilize MCMC optimization to fit a parametric model, shown here in orange, which is a combination of silicates and PAHs. Repeating this process for all spatial coordinates allows us to map the PAH emission along the long axis slit of the slit for 4 spectral bands, the 7.9, 8.6, 11.3, and 12.5 PAH emission bands. These are then used to reconstruct the radial PAH profile of the object. And now I'll present preliminary results for 2 of our targets. I'd like to begin with HD 169142. In this beautiful plot, the image is the scattered light image, courtesy of the Sphere Consortium. The yellow rectangle represents the mean orientation of the slit during observations, and best fit radial profiles of the 8.6 and 11.3, the strongest PAH emission bands, with the respective 1 sigma uncertainties, are presented as the white areas in the 2 bottom panels, which are of identical spatial scale as the image. The PSF at these bands is also plotted in the dashed line. You will see it better in a moment. Let's take a closer look at these PAH profiles. These 2 plots are identical to the ones in the panels to the left. As you can see, the bulk of the PAH emission for both bands is largely contained within the central region of the object, which is in the sphere images obscured by the coronagraph. Another interesting feature we explored is, following the reasoning presented in Maskant et al. 14, is the value of the ratio of the 8.6 and 11.3 micron banded densities, which is indicative of the measure of dominance of the PAH species, either ionized or neutral. Essentially, a higher ratio would indicate a greater presence of ionized PAHs. Here, we plot the 8.6 of an 11.3 emission amplitude ratio with its respective 1 sigma uncertainty region in white, with the best fit marked by the dashed black line roughly in the center, versus the intensity cross-section of the sphere image. While the best fit ratio value, marked by the dashed black line, indicates some increase in the ionized PAH presence further from the star, uncertainty rises pretty quickly and the radial trend cannot be easily determined. Another interesting object is 1 minute. We'd like to present is HD 97048. The plots are similar to the previous slide, with the exception that in this case, all images and graphs are scaled by r². For this object, a whole different trend is evident, of course. PAH emission is considerably more extended and reaches far into the disk. Not only that, but the emission intensity is noticeably radially asymmetric. The trend of the 8.6 of an 11.3 band ratio, however, is again quite open to interpretation. And with that, I'd like to summarize. And so in our study, we observed 8 Herbig Ae disks with VISIR-NEAR as a Longslit spectrometer. From these observations, we spatially resolved N-band spectra with a resolution of the order of tens of AU. We optimize these spectra for their constituents, including 4 PAH emission bands, and generate radial PAH profiles. We present preliminary results for 2 objects, HD 169142, whose PAHs are concentrated in the central region, and HD 97048, whose PAH emission is extended and exhibits radial asymmetry. And with that, I'd like to thank you and would be happy to take questions.
Okay, thank you. So we have one question from Mario. So how do you know that the PAH are ionized instead of different PAH sizes?
I suppose there is a measure of degeneracy between these 2 quantities. However, what was presented in the Maskant work is that specifically the 8.6 and towards the bluer region of PAH features, the larger their emission grows, the more dominant, the more indicative it is of a dominant presence of ionized PAHs with respect to, for example, the 11.3 emission.